Hi, everybody. Can you hear us? Yep. Thanks. Okay. So we're just getting started. The room we wanted to use was locked, so we had to find another one. But we're almost ready to start now. Let's start.
I'll do everything up till last release.
So the beginning.
I'll do the beginning all the way down.
Okay, sounds good. Okay. Well, let me just
I'm gonna be stealing both your computer and my computer so that I can look ahead on the chat. If you're okay with it. You can use my computer, it's also fine too.
Yeah, sure.
Yeah.
See the slides. We're trying. Oh no, wait.
Which one's your slides?
The slides are on the other screen.
Oh. Okay, that's fine. Sure.
Wait, I'll stop sharing then for a second. I'll just stop the mirroring.
That's fine.
Okay, now you should both be able to see the thing in.
Okay. Hi guys, sorry for the delay. Can you guys hear us well?
Yeah,
Hello. I was just about to get started. Yeah. So this is the cryptography final review session, and we'll just be going over some basic concepts. It's not completely comprehensive, but hopefully this would be a good way for you to get started on reviewing on cryptography. Feel free to raise your hand and ask questions if you guys have any questions. And we'll be working over some practice problems too. Yeah. So cryptography, why? We use it to enable secure communication. The goals is that confidentiality, adversary cannot read messages. Integrity, adversary cannot change the messages, and authenticity, that the message is from whoever sent it, who claimed to send it. And so one of the key concepts that you need to know is IND-CPA. And essentially how this game works is that Eve can send messages of her choosing to Alice to encrypt. And they basically can keep doing this back and forth. And once they've done that, then Eve can choose two messages, M0 and M1. And they're going to encrypt it. They're going to send it to Alice. Alice is going to pick one of these messages, encrypt it, and send the ciphertext back to Eve. Eve should not be able to based on that ciphertext, be able to determine whether it's M0 or M1. They will be able to have that oracle access and keep sending whatever messages. Even the same exact M0 and M1, they will send it, and that encryption should be a different ciphertext, so that there's no way for it to be able for them to be able to tell which original ciphertext is sent. And after it has this oracle access, then at the end, Eve has to decide, oh, okay, was this ciphertext a based on M0 or M1? And this is considered confidential if Eve's guess is accurate half of the time. And why is that? It's because if there was no way of it to know and gain any information, then it should be able to guess it with a probability of 50-50, just instead of having some way of being able to guess and have some form of advantage. EU-CMA and other similar schemes, you have probably seen this similar in past midterms exam questions. It's the same idea, except it's applied to signatures instead of max. Yeah. So let's look at deterministic schemes. Determinism is an encryption algorithm, which means that the ciphertext is always the same given the plain text. This is not IND-CPA secure. And the reason is because there will always be a greater than 50% probability of guessing the plain text. Basically, like, if you are able to have determinism, then when you play that IND-CPA, if you go back to the slide here, remember that we have oracle access in the very beginning and oracle access at the very end, in between that guessing of the game of M0 and M1. So if it was deterministic, in the beginning, before Eve sends like M0 and M1, there's nothing stopping it from asking Alice to encrypt M0 and M1 in the beginning and to encrypt M0 and M1 at the end after it had already sent that ciphertext. So if it was deterministic, there's nothing stopping it from using that oracle access part to determine if the ciphertext matched M0, M1. And then that just breaks the game because Eve will always correctly guess which message was encrypted. And so that's why deterministic schemes are never IND-CPA secure. XOR functions. So this is a little bit of a math, but it's really not too bad. Basically, XOR returns 1 if 2 bits are strictly different. So 1 XOR 0 is 1. 1 XOR 1 is just 0. And then we also have the commutative property. X XOR Y is the same thing as Y XOR X. Associative. And then if you XOR the two same exact thing, it equals to 0. If you 0 XOR Y, it's Y. This is good to know sometimes for some of the cryptographic problems that we have. So one-time pads. One-time pad, how it works is that we create a random n-bit key, where n is the length of your message, and we will always have a new key for every single message shared between Bob and Alice only. The reason why we need to have a new key for every message is so that there is no determinism. So encryption function is just K XOR M, and there's this bitwise XOR of the message M and the key K to produce the ciphertext C. And then the key is always different every time, hence the name one-time pad. Decryption is always the key K XORed by the ciphertext C to get the message M. So just like how we've looked at the XOR slide, why does this work? So K XOR C will be the same thing as K XOR K XOR M. And since K XOR K cancels out, then we just get the message M. So what's the problem with one-time pads? Randomly generating keys per message is really expensive. And the second question is like, how are you going to share the key ahead of time before you send every single message? Because if you have to send a message insecurely, you can't just send the key insecurely also through the same insecure channel, because then that defeats the whole purpose of one-time pads. Practicality, only practical if the keys are communicated securely in advance before channel becomes insecure. So because of that, in real life, we don't really use one-time pads. Rather, we can explore block ciphers and modes of operations. So block ciphers is basically, you're just encrypting a fixed size block of bits using a key K. Correctness, the encryption of K is a permutation, and then the decryption of K is its inverse. Yeah, usually if we give you a block cipher, you really don't need to know what's happening inside the encryption E. Just know that gets permuted. Efficiency, and that you can't figure this part out unless you have the K bits. Efficiency, and the encryption and decryption should be fast. Security, E behaves like a random permutation without knowledge of K. So I think these are like good assumptions to always have. But just because we have this does not mean that just using straight out block ciphers is secure. Why is this not IND CPA secure? This is because we never said that we're changing the keys every time, which if we were changing the keys every single time, then it just becomes another one-time pad. And remember again, IND CPA cannot be deterministic. But in this case, every time I encrypt the same exact message using the same exact key, I will always get the same exact ciphertext. So, like I mentioned, it is deterministic. It also has a fixed size encryption. And so how we solve these issues is by modes of operations. So we use the block ciphers as a building block, and we build upon that. So here's a very simple idea, which is an ECB mode. Spoilers, it is insecure. Basically, how they do it is just M is the number of blocks in the plain text, and they just send in message M0, M1, M2, and there's a key, and we have that encryption, and you just get the ciphertext. And then when you send the actual message, you just concatenate all the cipher block text together, and that's what it is. Is this IND CPA secure? No, because this is deterministic. One very easy way to see this is like if you say that the first word is hello and the second word is world, and then the second time I send in the message, it's hello, Andy, for a random message. Because the first cipher block is always going to be the same, C1 and C1 prime will be the same. C2 and C2 prime will be different, but you can make the message a little bit longer to be able to determine which block is which. So one common example is that, for example, if you were to encrypt this penguin image with the ECB mode, notice that you can still see the exact same structure. The color is a little different, but looking at this, you can guess that this is a penguin. Again, this is the whole idea of deterministic, right? The same exact black colors get encrypted the same exact way. And so these blocks look exactly the same. So does not hide the info. IVs and nonsense. So IVs is an initialization vector, and nonsense is number used once. So sometimes it's a little confusing. Kind of just see it as the same exact thing. Nonsense is basically an IV. And all you need to know is that it's just a bunch of random bits, typically generated uniquely on each encryption. The second most important thing is that they are public, and it's usually included as the first block of a ciphertext. And so anyone, even the adversary, can know what the IV is. CBC mode, this is another block cipher mode of operation mode. And how they do this is that they take in a plain text and they use an initialization vector. And then they XOR it before encrypting it. And they get the ciphertext, and they also use that ciphertext to XOR the next message block. And they keep going. Things to note, they do use padding. The plaintext must be a multiple of that block size. And then the decryption, how it works is just completely opposite. So they would start with the oldest ciphertext, decrypt it, XOR it by the previous ciphertext in order to get that plaintext. And then they repeat. So the second ciphertext would be decrypted and then XORed by the previous ciphertext, and you get that plaintext. So if we look at the penguin to see how this looks, you'll notice that there is no information now. There's no way to know the penguin shape. Each of these blocks look equally as random as the other. And so this would be a IND-CPA secure mode, block cipher mode. And the whole key to why this is not deterministic is because of the initialization vector. The initialization vector allows it so that even if I were to encrypt the same exact message, hello world, twice, my ciphertext will always be different. Because the initialization vector is always a random key that is, sorry, not a random key, a random number that's generated at the beginning of the encryption. And that means that when I encrypt it 2 different times, the initialization vector will be different both times. The CFB mode and another method. So they don't have to use padding, unlike the CBC mode, which is nice. And they also encrypt the previous block ciphertext. So they start with the initialization vector. They use that to encrypt. They use that as the message to encrypt. Then they XOR it by the plain text to get the ciphertext. Then that ciphertext is now encrypted, and you XOR it by the next plain text, and so on. So how would you decrypt it? So again, working backwards, you would XOR the last ciphertext. Wait, sorry, never mind. You My bad. Yeah, so you pass in the IV, you decrypt it, and you XOR it by the previous ciphertext, and you get the plain text. And then you pass in that ciphertext to decrypt it again, and then you XOR it by the ciphertext of the next one. So it's a little bit confusing, but CBC basically, the previous one was XORing it by CI minus 1, and then you decrypt the CI. But in this case, is the other way around. You decrypt the CI minus 1 and then XOR it by the next ciphertext. And then the third, also, this is also IND CPA secure. Again, the same exact idea is that the initialization vector is in place. It's not a safe assumption to say that, oh, just because there's an IV, therefore this block cipher mode is secure. But if there is no initialization vector, it is a pretty good sign that, or a pretty bad sign, that this block cipher mode is not that secure, or at least most likely not IND CPA secure, because initialization vector allows you to create that randomness. Counter mode is also IND CPA secure. This one, in my opinion, is the easiest to remember how to decrypt and encrypt. But basically, all you do is you have an IV number. Again, that's public. And then you're doing the same thing as a ECB mode. But the reason why this is secure is because the IV changes every single time for each of the new message block. So you start with a counter of 0, and each time you encrypt the next plain text message, you increment that nonce. And then after you encrypt that IV, then you XOR it by the plain text and you get the ciphertext. Decrypting is also a lot easier because all you're doing is decrypting that nonce with the counter correctly, and then you XOR it by the ciphertext, which will allow you to get that plain text. So some things to note, the nonce is public. The attacker does know the nonce. The attacker also knows the counter value. So why is this secure? It's because we are encrypting it still, even though because we encrypt the nonce and the counter, there's no way for the attacker to know what that encrypted value of the nonce is before we XOR it by the plain text. And so that's why this can still be considered secure. Because even if you were to try to XOR it, there's no way to XOR the ciphertext with a nonce if you didn't know what the encrypted value is. So if we look at the penguin, this again is also IND CPA secure. It is also random. Okay, so let's go through some practice problems. We're gonna look at some problem with question 1. You guys can quickly spend a minute or two reading through it, and then we can go through it. All right. So we can quickly go over this one. So how I would solve the first question on how do I decrypt it is I usually like to just work backwards. When I see something that's relying on the next or the previous ciphertext to XOR it or that type of thing, it's just nice to start working backwards. So I'll first look at C3. And I see that it's the before we get C3, we have to XOR it by C2. And so and then we work backwards, right? So, okay, I have C3 XOR C2, which would get me to where it's an encrypted version. So to get the decrypted version, I just decrypt C3 XOR C2 to get M3. Same exact idea for the second block, the block before it, so which is C2. C2, you just XOR it by C1, and then you decrypt all of that, and you would get the previous message M2. And so which of these corresponding decryption equation matches that? Notice we're doing the current ciphertext XOR by the previous ciphertext and decrypting all of that. And so the only one that makes sense would be A. DEF is already wrong because we're encrypting it when this is supposed to be looking for a decryption equation. B is incorrect. Sorry, because you are XORing it by the previous plaintext. And then C is just wrong because you're XORing it by both plaintext, which logically also doesn't make sense because why are you decrypting a plaintext XORed by a plaintext? But yes, hopefully that makes sense. And let's quickly look at 1.2. Alice and Bob are communicating using PFB mode, which is the mode that we just introduced. Alice encrypts and sends a 10-block message encrypted using PFB. Bob receives the message, but the sixth ciphertext block is lost in transmission. Which blocks of plain text can Bob recover? I'll give you guys a few minutes to also think through this. Okay, so how I would solve this is that you need to look at the decryption formula. Notice that in order to decrypt and recover the plaintext message, you are relying on CI and the previous block CI minus 1. So if I lost C6, I won't be able to decrypt plaintext 6 because I would need C6 XOR C5, but I don't have C6. And I also can't get P7 because to decrypt that, I would need C7, which I have, XOR by C6, which I don't have. But for all other blocks, because it's not dependent on C6, I should be able to get everything else. So J is the correct answer. 1.3, PFB is not IND-CPA secure. To prove this, the adversary will win the IND-CPA game against the challenger as follows. Sends two messages P and P prime. First message is 3 unique random generated blocks, which is of the following values of P prime would allow the adversary to win the IND-CPA game. Okay, so if you guys quickly took a look at it, we can also just do some level of deduction. C would be wrong because that P prime is the same exact message as P. It's P1 concatenated by P2 concatenated by P3, which if you're trying to pick the difference between one or the other, it doesn't make sense to send two same exact messages. We can also eliminate D and E because flipping some bits in that plain text makes it indistinguishable from random, and this will not help us distinguish the message that was encrypted because um, when you look at that block cipher, right, it gets encrypted. And so flipping that last bit or something like that gives us a completely different message. So now looking between B and A, B is not also going to help us because it's just another randomly generated blocks, right? Which is the same exact idea of P. The only way we can distinguish it is if there's a way where we can have like something that is repeated again and again. So A makes the most sense because P1 prime, P1 prime, P1 prime, um, you're repeating it, and that block cipher will produce the same output 3 times because the block cipher is deterministic. We can, yeah. So if you look at why this works, is because if P1 prime, P1 prime, P1 prime is right here, yes, the IV is going to be different, but what helps us to distinguish that from 3 randomly generated plaintext is that each of these ciphertext C1 will be exactly the same. We will encrypt that, and that encryption will be exactly the same. The first one will XOR by an IV, and you get that cipher C1. But then since you have the same exact P1 prime here that gets encrypted, and you XOR it by the same C1, then you're going to get the same thing here when you XOR it again by the same P1 prime. So that's the intuition that you should get. 1.4, the challenger sends back a ciphertext C, which is an encryption of either P or P prime. Describe a strategy that the adversary should use to deduce whether P or P prime was encrypted that would allow them to win the IND-CPA game with a probability greater than 1/2. So in order to solve this problem, you should not try to just make everything random. Rather, try to find a way where you can find some like repetition to be able to determine if it's P or P prime. So one strategy would be to XOR each ciphertext block with the previous ciphertext block. And if the plain text blocks are the same, then the results will be the same values. So you can look at C1 XOR C0. We're looking at the second half of this solution. So if you XOR it, and then you'll get EK of P1, and then C2 XOR C1. And then this is the same exact idea as earlier where we showed that P1 prime, P1 prime, P1 prime. Notice that you end up getting the same exact EK of P1. And so one way to win this IND-CPA would be to pass in P1 prime for all of the for all of the P, and then the other one would be a P prime that's random. And if the plain text blocks are different, then you can say that, oh, this will be like P prime or something like that. The other way is you can notice that there's this here. C1 equals EK of P1 XOR C0. C2 is just EK of P1 XOR C1. And then you basically can get IV in the middle, and then C1 and C3 is exactly the same. So as long as C0 and C2 equals the IV, or C1 equals C3 in this case, then we can say that, oh, the ciphertext has some way to learn information. Let me know if you guys have questions and if this is confusing. Otherwise, we will move on. So for 1.5 is asking which of the following are true about the PFB mode. Decryption is parallelizable. PFB provides integrity. The plaintext must be padded to a multiple of the block length, or none of the above. So what does it mean for it to be parallelizable? That means that you should be able to not have to determine, like, you don't have to rely on the previous block or the block ahead of it for its decryption in order to decrypt the current block. And if you look at this, how do you decrypt it? You need the previous ciphertext block and your current ciphertext block, XOR it and decrypt it, and you get that message. And so this is parallelizable because you're not waiting on C1 to be decrypted in order to decrypt C2, or etc. Does PFB provide integrity? No. Block ciphers in general do not provide integrity as a rule of thumb. And yeah, you could send two different messages and there's no way for the receiver to be able to determine who actually sent it. There's no marking in here. All this does is it's supposed to provide some sense of encryption. And in this case, PFB is not even really secure anyways. The plaintext must be padded to a multiple of the block length. This is true because the blocks have to be exactly the same right length. So if the message is a little shorter, you will have to pad the end of M3. Notice this is required because C2 and C1 is XORing for the next block. And so if C1 has this certain number of bits, C2 must have the same exact number of bits because we're XORing it. Same thing with C3, right? Or M3. If M3 is a smaller number of bits, we have to pad it because we're XORing it by C2. That's how we know that it needs to be padded. Okay, so we're going to switch gears and we're going to look at hashes and max, which is integrity and key exchange. What are hashes? Hashes is just like given an M arbitrary length message, the output will always be a fixed length n-bit hash. And it's going from 0, 1, like a arbitrary length message to a fixed length of n. And the properties of a hash function is that it needs to look random, but it is deterministic. It also needs to be fast. And then two really main things that you need to remember is that it is one way, which means that it is hard to find x given a y such that h of x equals y. And then also that it is collision resistant. Hard to find x does not equal to x prime, such that hash of x equals to hash of x prime. Sorry, I just saw a previous message on the previous problem that we worked. Someone asked me, how is this different from the two modes we discussed earlier that makes this insecure but the other secure, specifically CBC and CFB? That is a great question. So let's quickly take a quick review on CBC mode. Notice that they do look very similar. They have an IV, and they are relying on the previous blocks or the next block previous block to encrypt, right? In this case, it's a plain text, you XOR it by the IV, then you encrypt it, and then for the next message, you take the previous ciphertext, you XOR it by the plain text, and then you encrypt it. The key here is that before encrypting, there is some XORing that's going on. And so an attacker cannot XOR before looking at that encrypted block, right? And that makes it a little bit more secure. And then when you look at CFB, it does the XORing later, but because the IV is encrypted, and then you XOR it by the plain text, um, before passing it in. Like that, this is how this one works, right? And then now let's look at PFB mode. In this case, um, because that M1, M2, M3 gets encrypted, that encryption will always be the same. P1, 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 like it does, like M1, M2, and M3 can be the same exact P1, right? Which allows you to get the same exact encryption in the beginning. Whereas if you look at CFB, right here, we actually encrypt the IV in the beginning. And so this, even though I can do P1, P1, P1 again, because the IV is what's encrypted in the beginning, then it will always be different because the IV will always be different. So even though I'm XORing by the same exact message P1, because the beginning block is already different, there's no way for me to know. And if we look at CBC mode, yes, I am encrypting it by the plain text, but because it's XORed first before I encrypt it, that encryption block will always be different. So that's the distinguishment for why CBC and CFB is considered like IND-CPA secure, but then PFB is not. Let me know if you still have questions on this. Otherwise, I'm gonna move on to and continue talking about hashes. But that was a really good question. Hashes and integrity. For this example, assume that the hash M cannot be replaced and tampered with. So if the message is tampered and the hash of M isn't, Bob can compute hash of M himself and make sure it matches the same, the sent hash. So the idea of like how Max and everything all started is just like if Alice sends a message and it also sends a message hash of M to Bob, Bob can always recreate that hash of M to double check that that message M is what Alice actually sent. Now we're assuming in this case that that hash cannot be changed, that it wasn't replaced and tampered with. But the key idea is that Bob can recreate that check to make sure that that message M is from Alice. Now, this doesn't work because right now anyone can change this. Anyone can create that hash of M and just send it, right? Can hashes provide integrity? Not alone. Hashes are unkeyed, so anyone can compute the hash of any plaintext. So the solution is we're going to introduce something called MACs, message authentication codes. And how this works is that we have a message M, and there also again has to have some key K that is used for this MAC. And you pass in the message M and you get a tag. And then when you send it to Bob, you send this message M with the tag T, and Bob now verifies it using the same exact key K to verify that M is as it is sent by Alice. And more importantly, how this works is that you generate the tag T for message M using key K. The inputs is basically a secret key, only Alice and Bob should know it, and an arbitrary length message. The output is a fixed length tag on the message. So the biggest difference that you're seeing between hashes and MACs is that MACs uses a key. That is important because that means not anyone can just compute the MAC for a certain message. In order to be reasonably sure that the message in the MAC tag matches, it has to be generated by the same exact secret key, right? So if I have key 1 and key 2, and I use MAC on the same exact message, I should get 2 different tags. And so if I send from Alice to Bob and they both have the same exact key K, if I generate a tag, I should be able to prove that, hey, because we have the both same keys, if I generate this tag and I send it to you with the same message, Bob should be able to recreate it with the same key and get the same exact tag. So the properties of MACs is that it also has to be deterministic. Um, Actually, sorry, it has to be deterministic, unlike encryption. It needs to be efficient. And then the security is EU-CPA, which is honestly a very similar concept as the IND CPA. An attacker cannot create a valid tag on a message without the key K. In practice, we use HMAC. Now, the big thing that you need to remember is that MACs are not confidential because it is deterministic. So the authenticity for MACs is implicit because we assume that only Alice and Bob has the keys. Otherwise, makes no sense. Authenticated encryption. So there's two different ways. We have MAC then encrypt and then encrypt then MAC. The MAC then encrypt would be you MAC the message, then you actually encrypt the message. The issue with this is that you okay, well, actually, I'll tell you later. And then there's the encrypted MAC version, which is you encrypt the message, then you MAC that ciphertext of that message. Which one of it is better? I kind of gave it away. MAC then encrypt is not as good. Even though they are both technically IND CPA and EU CPA, the reason why we would never recommend using MAC then encrypt is that it requires a decryption before tag verification. What is the point of decrypting a ciphertext if you are not sure that the correct sender sent it to you, right? Like just in case Mallory sent a malware, like something bad that will corrupt your computer, it makes more sense to authenticate that Bob sent this message first before decrypting it. Because if you decrypt it and then it corrupted your computer, and then you authenticate it and you realize that it's not from Bob, it's a little too late. So it's just not the best practice. Always use encrypted MAC. It's more robust to mistakes. Passwords. Julien.
Okay. Let's see. So passwords. Try to stand up. So passwords are meant for authentication, for making sure that you're the person you claim you are. But given a password, how do you check if it's the right one for the user you're claiming to be? So one straw man is to just say, let's store the password in plain text. Given a username, just store the password and compare it. Problem with this is that if an attacker can access the database that contains the passwords, they can just get your passwords. And because people use passwords, which they shouldn't, that can have bad consequences beyond just your website. So the idea is that instead of doing that, you want to hash the password. Use what we just discussed, hashing, because if you find the hash of the password, you shouldn't be able to find the password, right? Well, the problem is you can still use this for brute forcing. The idea is because hash is deterministic and people use common passwords pretty often, you can just pre-compute these hashes ahead of time and then just see if they match. So that's what I just said. So basically, like, let's say you use the password. Well, if you just hash password, you'll see it's the same thing. So you'll still be able to figure out what password the person used. So these are dictionary texts where essentially you can just hash an entire dictionary of words of common passwords. If you look online, you can easily find the top 1,000 or 10,000 passwords. You can just hash those. You can also call these rainbow tables, which are pre-computed tables of hashes of known passwords. So hashing does help a little bit. If you use a password that's very unique that's never been used before, yes, it'll be really hard to reverse that. But if you're using a password that's just a combination of known words or a common password, then you're still back to square one. People can figure out what your password is. So to mitigate this, the most common approach is assault. Assault is a public random bit string for each user. And the idea is that you take something that's long and random, something that's public, and when you actually store your password, instead of storing the password itself or the hash of the password, you store hash of the password and concatenate with the hash. I'm sorry, the salt. Now, this seems like it's just doing the same thing, right? If you know the password and the salt, you could just recompute these things. But the problem is that if you don't salt, you could just do one single pass. You look at every password in a dictionary and then hash those, and that gives you the possible hashed passwords. But if you use a unique salt for each user, there's now m possible passwords, but n users. And so the complexity is now O of mn, because you have to do this hashing for every single user independently. Another, I'd say better reason than just this complexity is pre-computing these things, right? If I go online now and I type in MD5 hash rainbow tables, I'll get a pre-computed table of maybe the top million passwords. So I don't even need to do any of this effort. If anything is salted, even if the salted is reused across users, you can't use existing tables. You have to do the effort yourself. The best, though, is to use a separate salt for each user because it does go to this O of mn complexity instead of O of n plus n. So in practice, what does this look like? Well, let's say you have the naive default where you don't use a salt. You would store this in a table by having Alice and then the hash for password, Bob, etc. Now, if the attacker computed offline a rainbow table or dictionary attack, they can just look up in this table and see, well, what's the password that maps to this hash here, 8671W48, et cetera, and they can reverse the passwords. But now if you store salt with it and you hash with a salt, even if the attacker computed something offline previously without knowing the salts, it's not useful because they don't know the actual hash, the password with the actual salt, and so they can't reverse engineer it. Now, they would be able to do this if they just brute force through the entire database, computing for each user and each possible password, the combination of the salt and password, but that would be very expensive. It'd be O of mn, right? Okay, any questions about salting before I move on to the next topic? Okay. Slow hashes. So salting works well, but it only really brings the complexity from O of 1 if it's pre-computer, O of m plus n to O of mn. If you don't have that many possible passwords users and you have a very fast hash, you could still parallelize this. And with GPUs, you can compute like tens of thousands or like hundreds of thousands of hashes at the same time. So another mitigation here is to use a slow hash. The idea here is that if you use a slow hash, guessing the wrong password should waste time. Meaning instead of like, let's say, having a single millisecond between each guess, it would take up to when it's a full second. And that just slows down the attacker, even though they have to do the same number of operations before. Now each operation is much more expensive. And for a user, well, if you're logging in and it takes a second versus a millisecond, it's not a big difference in usability. Of course, like you'd rather not have something that's too long, but it's probably fine. Okay, let's go to practice problems. Oh, I see there was a question in chat. What happens when you hash the salts? So you don't hash just the salt, right? What you do is you hash a combination of the password and the salt. And the idea is that by doing that, you introduce some randomness into the thing you're hashing so that you can't just pre-compute these hashes ahead of time, right? So because you don't know what this salt value is going to be ahead of time, you can't ahead of time compute all the hashes, meaning you have to wait till you know what the salt is to compute your whole dictionary attack, which means for every single user, you have to recompute a whole dictionary attack, which is inefficient. Does that answer your question? Cool. Okay, so let's go to the practice questions. So I'll let you think about this for a second. Actually, this is the setup, so it's not the question itself. So we're going to imagine a password storage server where there's end users, and they choose their password from a pool of n possible passwords. Usernames are unique, passwords may not be. And we consider an attacker who can compute up to O of n hashes, so they can hash every password that's available. They can read and modify the actual database, so they can see what's happening and they can change it completely. And they can perform on offline brute force attacks. Clarifications don't really matter for now, so yeah. So for the first scheme that we're going to consider, what we're going to do is that we're going to store for every username the hash of the password and then a signature of that hash. The signature is computed over some secret key that only the server knows, and it's the same secret key for every single user. That's important. So let's try to figure out what happens. The first question is the attacker able to determine all pairs of users who share the same password? I'll give you 30 seconds to think about this and we can answer it. Okay, so for this one, the answer is yes without computing any hashes. The reason is that there's no salting happening, right? So two users that have the same password will have the same hash of the password. So you can just look up in the table which users have the same stored hash of the password, and that'll give you all pairs of users who share a password. You don't need to compute any hashes. You don't need to, well, yeah, it's just observe the data set. Does this make sense for everyone? Okay, so the next question is, and also feel free to interrupt me like later on if you realize it doesn't make sense, I can always go back to this. Next question is, how many users' passwords can the attacker learn? Now remember, the attacker is able to compute up to O of n hashes, so compute a hash of each password, and is able to read and write from the database that contains the passwords. I'll give you a couple seconds. I'll make this interactive. Who wants to answer? Sorry. Which one do you think? Is it D, E, or F? Yep, all of them, because they can just compute the hash of every password and then just match it up in the database, right? And finally, what can an attacker do to a specific user's password? This is a little more tricky. Remember, they can change, read and write to the database, and they can compute any hash value. You want to give it a try again, or do you want me to answer this one? G, exactly, yeah. No, the reason why it's G is, and this is kind of subtle, they could replace everything in the database with something else, right? And they can compute hashes as passwords, but they don't know the secret key, so they can't sign any arbitrary password. However, they can take the value that's stored in somebody else's password. So like, let's say there's multiple users. They can take the hash of the password of user of Bob and the signature of Bob and replace Alice's entry with this. And because these signatures are not per user, but they're just using a single secret key, the like we won't be able to tell that they changed this. So that means they can change to a specific value, but not necessarily the attacker's choosing. It's just any value of another password somebody has. Okay, does this make sense? Okay, cool. Let's move on to the next part. So now the system is a little bit more complicated. We're gonna, instead of storing the hash of the password, store the HMAC, so the tag, associated with string username, concatenate 161, concatenate with password, and signed with a key, sorry, computed with a key K that only the server knows. Now, same question as before. Can the attacker determine all pairs of users who share the same password now? Annabella. I'm kidding.
Yes, without computing any hashes.
No, you failed the class.
Wow, how I
So the reason it doesn't work here is because even though the key is the same, so like you could assume it's the same as before, the string you're actually macking contains the username, and we said the usernames are unique, which means for two different users, they will always have like a different prefix to their password. And so it won't be possible to figure out which users share anything. Because like for a same password, um, because the username is going to be different, they'll just have different HMACs. Now, that being said, this is not the best scheme, and we'll see why. I don't want to. I'll foreshadow a little bit. Concatenation is always kind of tricky to do. And yeah, computing hashes here doesn't help. I mean, it's not a hash; it's an HMAC, and yeah, you just can't compare the values because the username changes. Okay. Oh, sorry. Well, I spoiled it by mistake, so I'll just go to it directly. How many users can you learn? Well, none, because you don't know K. And so you can't compute any HMAX, meaning you can't, like, you're not able to compute the actual, like, image of any password. So, like, even if you know every username, and you list every password, you'll never be able to reconstruct the HMAC without knowing the key. And you can't reverse the HMAC itself. The HMAC is based on a tag, on a hash, so like you can't actually reverse the function. So there's no way to learn anything here. Let's see, there's a question. Could 3.1 be done in O of n squared? Could it be done in O? So it can't because of K, yeah. But it's a good question. So if this was just a hash, then yes, you could compute O of n squared hashes, basically for every user and password. And well, you'd be able to figure out exactly which user has which password, and then you'd be able to like not only find the pairs, but also reverse engineer which passwords they have. Because at K, you can't do that. Now, it is still possible to do something, and we'll see this in one of the next parts. Okay. So, we now have a slightly more complicated system in which we have the same like username slot like 161 password structure. And this is not a slot, but this is like it's not really visible, but like these are just concatenations. And you store the encryption of that using a key and then the HMAC of that thing. So basically authenticated encryption of this content. Now, unlike the previous one, now it's recoverable. Like if you know the key, you would be able to decrypt this and check it, right? So there's two ways the user can interact with this password server. The first is they can create a new user. So for a new username that doesn't exist and a new password, the server computes these values and stores it, and now there's a new user. And for logging in, the user provides a username and a password. What they do is that the server's first going to make sure the ciphertext is valid, hasn't been tampered with. It's going to decrypt that ciphertext and compare the plain text with the string username 161 password. And if that's correct, then perfect. The user can log in. Now the attacker can perform both these operations. The server can ask the server to create users. It can log in as a legitimate user. It can also read and modify the database at all times. It doesn't know keys K1 and K2 though. Okay. So with this setting, and I'm not sure the clarifications really matter for now. This setting, the database contains one user, Alice161. So the username is Alice161. The attacker does not know their password. Explain how the attacker could log in as Alice161. Remember, the attacker can read and write to the database, and they can create new users, and they can log in as a user if they know the password. And they don't know the keys K1 and K2. So for this one, I'll give you a little bit more time, maybe a minute or two. It's a little bit more involved, but this is going to go to the heart of why I was saying there was an issue with the previous scheme. And one thing you can try to do is to just write out what string will be encrypted for LS161. Like, so just like pick up random password and see what string gets encrypted. Okay, I'll give you a minute or two. And then maybe raise your hand when you have a solution, and then I'll just wait till half of you have your hand raised before, or when you give up if you can't figure it out, so we can go over it. Actually, maybe I should do it for the sake of time, just to make sure we don't go over. Okay. So any ideas on how we can do this? Okay, so it's going to involve some interesting string manipulation. Let me close this so we can actually see what's happening. So what you're going to want to do is to create a new user with username Alice, right? The username before was Alice161, so that's valid. And set the password to 161 known. What this creates is that this is going to cause the server to encrypt and back the string Alice. If you can't do it with 161, can't do it with the password, which is 161 known. And then the attacker can see the resulting ciphertext and back, right? Now, why is this useful? Well, it's because if you look at the original user, Alice161, Alice161's string was going to be Alice161, 161, and their own password. So using this, the attacker can just copy the encryption MAC of the new user to the old user. And now the attacker can sign in with username once Alice161 and password no. Because this has the same structure as username Alice161, the separator, and no. Now, what this shows is that when you're concatenating values in like some hashes or anything, and because it was kind of similar in project 2, be very careful to make sure there can be any collisions. Because this is a typical collision. It's saying the 161 in the username can get mixed up with the 161 in the separator. Which means that in this case, originally there was Alice161 and then the separator 161 and her password. But what we did here is that we created a user called Alice with password 161. And so the first 161 becomes a separator and the second one becomes the password. And so it's basically by doing this manipulation, we're able to like change where the boundaries are in our separator and actually create an entry, a password entry that's valid for Alice161, but with the wrong password. And now we can just log in. Does this make sense? Okay. So using this, now we'll try to do the next one, which is pretty similar. And so I'll let you try this one. And yeah, try to use it should be a similar idea, I think, to the one we just talked about before. I'll give you a minute. Okay, let's try to figure it out. Any ideas on how to do this one? Yep, that's the idea. So you create a username with evanbot161 and then a password known. And this entry is now going to look like this. It's going to be evanbot161, 161 known, which in this case, the username is evanbot161, separated is 161, and then the password is known. But you can reinterpret this as username evanbot, separated 161, password 161 known. So once you have this, you copy this entry to Evan's bot's original entry. And now that means you just change the password to be 161 known. Does this make sense for everyone? Cool. Okay. Let's move on to Diffie-Hellman. If you have questions about passwords, just put them in chat or ask me and I can go back to it. So, one common problem before I go to the actual thing with in crypto is how do you establish trust at the beginning? How do you like share something at the beginning, right? And how do you share something between two parties without an eavesdropper being able to hear about it? And Diffie-Hellman is a typical example of a key exchange algorithm, a way to exchange a secret to somebody else that nobody else can know. So the way this works is that Alice and Bob both generate a random number, a secret key. So Alice generates A, Bob generates B. And then the like protocol will decide on a common value G, so some sort of like some random value, I mean not random, but like some value G, some group element G. And both compute G to the power of their secret key. Now the idea here is that all this is like group arithmetic. So these are typically huge numbers. And they do this mod P, so they do this in a field, like a prime field of order P. And a lot of these things, like we're always working in prime fields. And this is their prime public key. So the thing is that if you know the secret key A, you can easily compute G of A. You can do it in log time by doing fancy exponentiation. But if you know G of A mod P, so if you know the like exponential group element, it's really hard to go back to A. This is the discrete log problem. So you can't really go back to the secret key from the core key. Now the magic of Diffie-Hellman is, I'll get to your question about the password in a second. I'll just finish this slide. The magic of Diffie-Hellman is that if I have Alice send Bob her public key and Bob send Alice his public key, they can now compute this value G of B to the A or G of A to the B. So which is actually equal to G of A times B. Because they know their secret key, so they can just take whatever they receive from the other side and exponentiate it again to their own secret key. And because you can commute exponentiations, G of A to the B or G of B to the A is equal to G to the AB. Now this is cool because now they share this value. They both know G to the AB. However, somebody in the middle only has seen both public keys. They can go back to A or B because we know there's discrete log. And they can't, if they multiply them together, that's G to the A plus B. It's not G to the AB. So they have no way of actually figuring out what this key is. And this is a basically a very simple idea that is used in a lot of crypto for making sure that only people that know the original secret are able to compute something, but nobody else can. I'll just go back fast to the passwords because there's a question. So in our specific example here, there was no delimiter between the username 161 and the password. So the format is just there's a username, there's a 161, and there's the password. And because you know the username, so like when you're actually doing a logging in, you provide the username, the server will go to that username things, decrypt, sorry, the string, and then match is my first part of the thing, the username, followed by 161, followed by the password that was provided. So essentially, you just reconstruct the string you expect to see, the Evan bought 161 known, and you just make sure that's the thing that was stored. You could if there were additional separators like slash and things like this, you could also do this. You just have to like craft a little bit more carefully. The only like good way to do this is through hashing. You hash the username, hash the password, and then you concatenate both. Because there's no way there to actually be able to like manipulate the strings. So it's just like basically you just reproduce this procedure generating from a username and a password the string, and then you just compare the strings. Does that answer your question? Cool. Okay. So, Diffie-Hellman. So I find this incredibly confusing, this slide, so I'm going to skip over it. The color stuff, like I don't know why this helps understand what happens. I think this is a more mathematical and with more principled explanation, and yeah, it's not very complicated math. So why does this work? Well, if you take G, which is like a random field element, a very large prime. So like if you work on like FP with P, like I know one of the largest primes we know. If you compute G to the A mod P for a random A, it's really hard to find A. It's what's called discrete log. The other reason why this works well is it's ephemeral. I can't say the word. You discard all this stuff when you're done. So you do this once, you exchange some information with the secret key, but then you never actually store A, B, and G of A, B anywhere for a long time. And so that gives us what we call forward secrecy. Even if a future secret is stolen, so like some secret in the future, like I know some information you exchange is stolen because you never actually stored A, B in the shared secret. You can't decrypt old messages. Now, if you were able to get both A and B and everything, yes, you could just reconstruct it. But if you just get one of them, well, because nothing's actually stored, you would be safe. So, using this construction, using this discrete log problem, we're going to build some crypto that's going to give us a new construction called public key cryptography. The idea here is to say, okay, instead of having a single key like we had before, each individual has two keys, and this is similar to Diffie-Hellman. They have a private key, which only they know, and the public key that is known to everybody. And typically, not always, but like you can always think of like the public key doesn't allow you to get the private key, but sometimes the private key can allow you to get the public key, like in Diffie-Hellman. And this pair is always like they have some sort of relationship with each other, meaning that you can use the public key to encrypt things and then use the private key to decrypt. And the nice thing is that this means you don't no longer need to assume that the people that are involved in a communication share the same key. Like in Diffie-Hellman, they can have different secret keys, but they can still share information secretly. It's much slower than symmetric key cryptography, and also it doesn't support messages as large, and also it's less secure. When I say less secure, I mean it's slightly easier to break public key cryptography than symmetric key. Mostly because the algorithms, like there are some better than brute force algorithms to do this. Not much better, but better. And also through quantum computing, we know that there is an algorithm, Shor's algorithm, that allows you to break discrete log and break RSA as well. So like all these factorization problems. Now there isn't a quantum computer big enough to do this yet, but the day there is, essentially all of traditional public key cryptography will be broken, which is why there's a whole area of study called like lattice-based cryptography, which is post-quantum secure. Anyway, that's the whole quantum stuff is not on the not needed for the exam. So the thing is that what we had before was Diffie-Hellman, which allowed us to create a shared secret, but it's not actually allowing us to directly encrypt a message and send it to somebody. But we can modify it in smart ways to get this property, to be able to actually make this into like a cryptographic like signing system and encryption system. So the way this works is that Bob has a private key B and then a public key G to the B. So this is the same as for Diffie-Hellman, right? And Alice has a private key R and computes her public key. I don't know what it's called, but like yeah, computes her public key G to the R. Now, this is the same setting as Diffie-Hellman. Where it changes is that now Alice, instead of sending just R, which she sent before, she's also going to send a second encryption, which is the message she wants to send times B to the R. So B is Bob's public key, and B to the R is Bob's public key to the power of Alice's private key. Now, why does she do this? Well, because let's consider what if Bob takes these two values, Bob can actually recover M. And nobody else can, right? If you look at C1, it's R. You can't go back to R because it's a discrete log. If you look at C2, it's M times B to the R. Even though B is known, you can't, like, B to the R is going to look random because you don't know what R is. And so this whole thing is going to look random, so you have no way to actually recover what M is if you don't know any other information. However, if you do know little b, so like Bob's private key, you can reconstruct what B was, what B to the R, and then you can reconstruct the message. The way this works is that you just take C2, so your encrypted message, and multiply by C1 to the minus B. What this does is that this is M times BR, so which is C2, times R to the minus B. But R was G to the R, so that means it's M times G to the BR times G to the minus BR. So these two cancel and you get back with your message. So it's this like a slight variation of Diffie-Hellman, where you still leverage the fact that both parties can compute G to the AB. The difference here is that you don't need to like first compute a secret, then use that secret to encrypt something. You can directly pass a message by leveraging the same property. So computing inverses is not hard. It's this discrete log problem. So essentially, this is answering a question online. If you know C1, you can compute C1 to the B easily. You can also compute C1 to the minus B easily. The reason for that is it's easy to inverse a value. Like if you have X, you can do 1 over X pretty easily. In these fields, I'm not saying it's true in every single possible field. And actually, we'll see an example where it's not easy later. And then you can just compute that to the power of B. What's hard to do in this setting is discrete log, which is given C to the A, figure out what A was. Inverses mod P is not hard. What's hard is going to be, we'll see later for RSA, inverses mod N, when N is a factor of 2 primes when you don't know the primes. If you know the primes, it's easy. I believe it's, sorry? Yeah, but I forgot the name of the algorithm to like do this. There's some Euclidean algorithm for like division that you can just use. I forget exactly which one. It's cool stuff though. It's interesting. Like this is where the math gets interesting, and it's not just CS. Anyway, so now AlgoML is cool, but not really used in practice that much for a bunch of reasons. But mostly it's malleable, which you'll see RSA also is, but like it's easier to fix RSA. Malleable means you can just like if you multiply C2 by something else, you'll get the encryption of like by 2, you'll get the encryption of 2M instead of M. And so that means like you could potentially abuse this and start like changing the stuff that it's being encrypted. RSA is what's more used in practice. So the idea here is we're not going to rely on discrete log as a hard problem. We're going to rely on factorization as a hard problem. So you take two very large primes, P and Q, that you choose randomly, and compute N. That's the product of both. Now, if we look at all numbers from 1 to N, basically, or to N minus 1, well, 0 to N minus 1, there's no longer a field in the same sense as before, but like it's a group, I think. And it has different properties. One of these is that if I choose E, which is a number that I'm going to take that be relatively prime to P minus 1, Q minus 1, and E has to be larger than 2, smaller than P minus 1, Q minus 1. I can easily compute its inverse. So again, this is the inverse. The thing I said was easy before. In this case, we're not in a field. We're in this sort of like this group structure, which is a group of like up to n. If I know these two primes, it's easy to compute the inverse. Use an extended Euclid's algorithm. But the thing is, if I don't know these primes, it's now very hard to do this. There is no like easy algorithm. Every algorithm that we know to be able to inverse something relies on the fact we know the primes that are involved. And so we're going to use this. And we're going to use this by using as a public key n and e, and as a private key d, d being the inverse of e. Now, why does this work? Well, for encryption, given I have a message, the encryption is going to be the message to the power e, modulo n, but all this is modulo n anyway. And Bob to decrypt is going to take the message. Sorry, it's going to take the ciphertext C and put that to the power D, which is the secret key, Bob's secret key, which like only Bob knows. Now, why does this work? Well, if you look at what C is m to the e. And so m to the ed, because e times d is equal to 1 in mod n, is just equal to m. Now, this shows why it works. We're going to show here why it actually like provides security. I mean, it's just basically without D, you can't actually do this, and finding D is really hard. And the reason why D is inversible, I mean, we're not going to go into that either, but essentially it has to do with the fact that we know the characteristic of n, which is p minus 1, q minus 1, and we can use that to compute what D is. Any questions about RSA? Is this NCPA secure? Do you think it is? Do you think this is NCPA secure? Essentially, under chosen ciphertext, chosen plain text, can you distinguish between two messages? And the main question here that we're going to ask is this deterministic? For a given message M, am I always going to get the same encryption? For also, a fixed key pair, right? Yeah, it's always the same, right? You just do M to the E, so like for a given key and a given message, you always get the same thing, which means it's deterministic. Because it's deterministic, it's not NCPA secure. So for RSA actually being deployed in real life, you have to add IVs, not just basically all of the bells and whistles we add to crypto to make sure that it's not deterministic. The nice thing here is that it's, well, another issue with RSA is that it is, what's it called? I'm not sure if this is called it's malleable in this case, but basically if you multiply, it's homomorphic. If you multiply two encryptions together, you get the encryption of their product. So if I have M and N and I multiply them together, I get the encryption of MN to the E. The problem with that is that means I can like still do some weird stuff with multiple ciphertexts to build other valid ciphertexts. I forget how we actually deal with that in practice, how you actually remove the homomorphic properties, but it's important to like remove them to make sure it's secure. And actually, that's typically a very common exam question is like working on these things. So, okay, I'll move on to digital signatures. So signatures are the equivalent. So like public key encryption is to like regular encryption, what signatures are to HMAX. It's a way to provide integrity and authenticity in a public key setting where each individual has two keys, a verification and signing key. The verification key is known to everybody. The signing key is only to the individual. And they can use the signing key to sign a piece of information so that everybody else can verify it came from them. And so it's essentially similar to an HMAC, given it was signed with the right signature key. Anybody with the verification key can make sure that this is a valid signature, but if the message is different, it's going to fail. Okay. I'll move on to the next part on key distribution. So we talked about a bunch of stuff here, including Diffie-Hellman, which is like a way to derive a shared secret. The problem is that there's still an attack against the Kalman, which is you can just have a man in the middle, right? You can sit in the middle and like intercept stuff. And so the way to get around this would be to say, okay, I would like Bob to already have some sort of key that I know to sign their key to say that it's valid, right? But it's kind of a bootstrap problem because to do that, you need to have another secret with Bob, which is like already knowing you need to already know their public key. And for you to get this securely, you need also have a secure channel. So like you're kind of like stuck, right? And so this is the problem with key distribution. How do you make sure that everybody knows everybody else's key and knows that's their key for sure? And if you have that, you can build all the rest of crypto, but without that, you can't really trust anybody. So that's kind of what I was saying. Bob, like if Bob just signed their own public key to send it to Alice, well, great, but Alice doesn't know Bob's public key yet to verify the signature. So you kind of like you need to bootstrap this. So you need to trust something. You have to have some root of trust. Yeah, trust anchor. Now, one technique, and this is actually something that is pretty common, is trust on first use. This is what happens on SSH, for instance. If you connect to an SSH server, it's going to ask you like, oh, you've never entered the server. Do you trust it? Here's its signature. This is saying the first time I reach out to Bob, I'm just going to trust it's Bob. Now, it's not perfect because, of course, if there's an adversary, then you're screwed. But if Bob is the right Bob the first time, then you're safe for the future. But the better way to do this is to do this through certificates and through or like established authorities, which hint is still trust and first use at the very core of it because there's no other way to do it, but it's a better way of doing it. So the idea is that a certificate is a signed endorsement of somebody's public key. It's saying I attest that Bob's public key is this, and it's signed by some sort of authority. And the key thing here is the authority is somebody that is not Bob, but that you trust. So if we trust EvanBot and he sends the fact that Bob's public key is whatever, then we can trust the certificate, right? So there's different ways to do this. Either you have a central authority, a central directory that contains all of these certificates. So that means, let's say, like you buy your computer from Apple and you trust Apple, and Apple signed, here's the certificate of everybody else on the internet, right? That could work. The problem is that with that is like Apple would have to sign every single certificate, which would be a pain. And also, if Apple gets compromised, then you're kind of stuck. A more realistic way of doing this is hierarchical trust, and that's how it's actually done on the internet. There's one root CA, so there's still one root to the beginning that signs other authorities. And then those authorities can sign in turn other people's things. So to check something, you just look at the certificate that's being signed by somebody, and then you go to that somebody that signed the certificate, check their certificate until you get to the root, which is somebody you trust. The reason for this, you can distribute these things, and also if one CA gets compromised, one of the ones that's like down on the leaves, then yeah, everything they've signed is going to be revoked, but it's only going to affect that part of the tree and not everything else. Of course, it still means that the root certificate is very sensitive. See Berkeley here, for instance. But what you do is that you only have this one sign very limited certificates and very rarely to make sure it's not exposed and the key doesn't get leaked. Key leaks do happen though. It has happened in the past that like major CAs get leaked and then you have to revoke basically millions of certificates. The idea here is that in this tree, you're going to have, well, I feel like this is kind of misleading. Campus Lab could very well sign Corey Hall. There's no reason why it couldn't. It's just in this specific tree, Corey Hall is signed by campus buildings, which are signed by UC Berkeley. Now, why Corey Hall not signed by campus? That's just like some rule that people sign it, but like it's not. I mean, there's no fundamental reason, right? The main thing is just remembering there's this tree structure where leaf nodes, which are users or websites on the internet, are assigned by intermediate CAs that can then go to the root CA. And there could be multiple layers, not just like it's not just two levels. Okay, we're gonna go to the last practice problem, I believe. I hope, otherwise I'm too late. Yeah, this is the last one. Which I think is kind of tricky. I forget. Yeah, but it's fun. So I'll go over the problem and then we can think about it together. So this is about oblivious transfer, which is still a very active area of research. The idea here is you, as a user of a popular document storage website, you want to access one of two possible documents, M1 or M2, but not both. So you don't want to access both of them and download them both, but you don't want the server knowing which one you accessed. The reason I say not both is that otherwise there's a very easy method which is just access both. And you don't want the server to know which one you're actually accessing, so you want to use an oblivious transfer scheme. We're going to consider one of two for now, but we'll extend to one of three in a second. And the user can access either one or M1 or M2, but not both. So the setup is you have a server and a user. The server is going to choose a random number A. Again, we have like a very large prime, like usual, and we're going to do Diffie-Hellman type stuff. The server chooses a random number A mod P and then sends a public key capital A, which is G to the A. Okay, so this is similar to Diffie-Hellman. The second step is then the user chooses a random number B, a small one, and the user knows which document they want, if it's one or two. So if I, which is the document they want, is one, they send B, capital B equals G to the B mod P, so like the standard public key of Diffie-Hellman. But if they want the other document, they want document two, instead they send capital B, which is capital A times G to the A, G to the B. It's a slight difference, right? These are both indistinguishable. Like from if somebody doesn't know what B is, well, like lowercase b, G to the B is a random value. So B or A times G to the B are indistinguishable. You can't tell which is which. The server now computes two values. A first key that's B to the A. So capital B to the A. And a second value K2 is B over A to the A. Which doesn't make a whole lot of sense now, but it'll make sense when we try to figure out how we do this. And then they send C1, which is the encryption of the first message under K1, and C2, which is the encryption of the second message under K2. And now, through some magic that we'll figure out, we can recover only the message we care about. Okay. So before we get to the actual scheme, the entire scheme, let's look at some warm-up questions. So if I equals 1, what value does the server derive for K1? And actually what I'll do is I'll give you 2 minutes and just try to answer all these 4 questions. And then we'll go over the results.
Hmm.
Okay. Anybody want to give an answer for Q2.1? Including online, if you want to just try it out. Yep. Its question is it's A. Is there an explanation? No, there's no explanation. Yeah, so it's A. For the second one, B up. For the third one, C up. And then for the last one, okay, I'll let you try to figure it out. So yeah, so for the first one, that was B to the A. And in the case of I equals 1, B is equal to the G to the B. So that's just G to the AB, which is the traditional like Diffie-Hellman like shared secret. For K2, we had B over A. So B is G to the B. A is G to the A. So we have G to the B minus A times A. Sorry, to the A. So that's G to the AB minus A squared. So not our Diffie-Hellman secret, but something else. Um, Crucially, that's something that the second value B is something that the server computed, right? But the clients can't compute because the client doesn't know A. And so they can't compute G to the A squared. The third for C, so if I equals 2, B is now equal to G to the AB. I forget. No, A times G to the B. So it's equal to G to the A plus G to the B. And so if you put that to the A, that's G to the AB plus A squared. Again, something the server can compute because they just computed, but the client can't compute because the client doesn't know what A squared was A is, so they can compute A squared. And for the last one, what's the answer? A, yep. If I equals 2, then B is equal to A times G to the B. So B over A is equal to G to the B. So you're back to your Diffie-Hellman that both users can compute. Now that means if we look at this, right, for question 2.1 and 2.4, we get back the actual Diffie-Hellman secret that both parties know. But for 2.3 and 2.3, we get something that one of the parties, the user, can't derive. What does this mean? It means that maybe we can, by using this information, we can figure out how to actually decrypt it based on the fact that two of these cases led to shared secrets, two of these led to something that's not shared. So given that, try to come up with an expression for KI, so the ith document key, in terms of all the other stuff. I find this formulation very confusing but basically try to figure out here, if we go back to this part, what part 4 is. How does the user actually decrypt the message they care about? They've chosen message I. How do they actually decrypt message I? Oh, yeah. So I'll give you a minute to try to do this. Okay, time's up. Any ideas on how to do this? What key should we use to derive the document we care about? And how can we build it? So remember, if we go back to the schema here, the server returns C1 and C2, which are the encryption of M1 under K1 and M2 under K2. So the user is going to choose either C1 or C2, depending on which message they care about, and decrypt it, but they have to derive this key. So what is the key they need to derive? It's A to the B. Now, why does this work? Well, if we look at the different cases, so the first thing we know is A is always G to the A, so that's helpful. So A to the B is always G to the AB. So A to the B is always going to be the Diffie-Hellman shared secret, right? And as we saw before, for I equals 1, the first message matches key, like K1 is G to the AB. And for I2, the second message key is G to the AB, which we just derived in this one, right? And so by just using the shared secret, we can now decrypt that message. We can't decrypt the other one, but we don't care because we only care about decrypting a single message. Does this make sense? So it's just basically Diffie-Hellman, but like with this added like decision here based on I to like either encrypt one or the other. But from the server's perspective, they're just doing the same operation every time, so they don't know which one you're actually going for. Crucially, because the server doesn't know what B is, the public key of the actual user, that they can't tell which of them is the shared secret and which of them is something else, right? Okay, so let's move on to the next questions. Um, why does the server can't, well, I kind of already said this, but well, I'm not really sure. I haven't really answered this. Why can't the server know which document the user has chosen to read? Is it because B is randomly chosen? So G to the B mod P will look random to the server. Is it because the server can't solve discrete log, or is it because the server can't tell the difference between G to the B and A times G to the B? And hint for this, there's actually two that are possible answers, but one that's a better answer. Okay, I'll probably just give the answers here because there's a last question that I want to get to that's interesting. So here it's C. Now, technically A is true, and that's what I just said. Because B doesn't know the shared secret, G to the B looks random, right? And because G to the B looks random, well, actually, the fact G to B looks random doesn't really, we don't really care about that too much. What we care about is B is randomly chosen, which means C, the server can't tell the difference between G to the B and A times G to the B. Because they can't tell this difference, they don't know which of the secrets they generated, which of the keys is the one that A can read and which is the one that A can't read. Now, which option best describes why the user is not able to read more than a single document per request? Well, this is B. The user can't derive G to the AB plus or minus A squared because they don't know A, right? They need to be able to get A to be able to do this, but A is what the server knows. Okay, based on this, let's try to extend this to 3 documents instead of 2. So we keep the same steps 1 and 4 from the previous scheme. So we still decrypt using the Diffie-Hellman secret, and we still have the server send A, which is G to the A. But now we're going to change steps 2 and 3. So for this first part, the user chooses a random number B. If I equals 1, they send B equals G to the B, like before. If I equals 2, they send B equals A G to the B mod P, so the same as before. But if I equals 3, what do you think they should send? And I'll give you a hint here. We're going to assume that A is prime. Well, A is always prime because we're in a prime group. So that means because of Fermat's little theorem, the only way to like A to the 1, A to 2, A to the 3 is always going to be a different value. It's going to be cyclical. You can actually generate all of the group using A. So A is a generator for that group. So the only way to get A to the N equals 1 is if N equals to P minus 1. So the order of the group minus 1. Which is Fermat's little theorem. So that means A squared is not equal to 1. So any ideas on what we can set B to? A squared G to the B. Why? Well, because if I look at A, right? Capital A is G to the A. Capital A squared is G to the A squared. So it's G to the 2A. Where is it? Well, we'll explain why it actually works for the second. But essentially, same as what I'm saying, 2A is also not going to be like it's also cyclical. So like there's the same property. For this, oh wait, I didn't want to give the solution here. So okay, so we have this new B. Now for the step 3, the server is going to compute 3 keys. K1 is the same as before, K2 is the same as before. And what should be K3 then? If we kind of mirror what we just said for question 2.8, what should we set K3 to be able to decrypt message 3 if I equals 3? Yep. Oh, yep. So B over A squared to the little a. The reason for this is that we want in the case 3 to be able to recover, to make sure that the key used for document 3 is G to the AB, but B is A squared G to the B, so we want to divide by A squared. And so the proof correctness is the same as before. Um, Now, if we derived all these things, like now we have a squared, so like the other ones would be plus or minus 1 or 2a squared, right? That would be the gap. And again, because it's a group and everything works well, I mean, this is actually a field, sorry. Um, like to be able to get n times a to be equal to 1 or to 0 to something deterministic, you need to actually multiply it by like p times a. So like this means you could potentially you could expand this to be instead of 2 or 3 documents up to p documents, where p is the prime. Not 100%, like I'm 90% sure of this fact. I haven't thought it out completely, but I think so. Anyway, any questions about any of the things we've talked about today? Okay, I see there's a question online. So the main idea here, this was okay. So the main idea is, it's always that like, given you choose your document I, only one of your like, and then you derive the keys. Only one of the keys is going to be the key you're expecting to have, and all the other keys are going to be impossible to derive because they all depend on some factor times a squared. Now, this works. So I originally was talking about exponents of stuff. I was getting mixed up between exponents and multiplication, but you can do this up to p elements because in your exponent we had earlier, right? Um, the one that we don't use is g to the ab plus or minus a squared, right? A squared is a field element. It's a field element in this field, so like a squared, 2 times a squared, 3 times a squared, all of these are non, they're not equal to 1 or or 0, sorry, they're not, none of them are equal to 0 because it's prime. But if you take p times a squared, because p is the order of the group, that's going to be equal to 0. And so that means that if you want to encrypt, do a one out of p documents, then you would have 2 documents that are decryptable, the one that you're looking for, but also the potentially one that is just like offset by p. And that one you would get g to the ab again. So you would be reading the key, and then you wouldn't get the 1 out of p, but you get actually 2 out of p. So, and all of this is rooted in some like algebra. So the idea here is you have your fields, FP, like usually call these FP. FP is a field of order P, so it's basically all the elements from 0 to P minus 1. And you can add a field structure where the addition here, I don't know if you like this is like algebra stuff, but if you look at the field structure, you have addition. I mean, you can add 2 elements, subtract 2 elements. So like A plus B equals A plus B, right? And then you can have a multiplication operation, which is just A times B. And the nice thing about, and like if you look at all the requirements for a field, this is all going to match. The specific thing with a finite field of order P is that there is no, the inverse for addition is, well, basically like we talk about generators for groups and fields. The generator is an element such that if you take the element, multiply by 1, 2, 3, 4, 5, you'll get distinct elements until you get, and the only way to get back to the original element is to multiply by the order of the field P. And you call the generator because like if you take an element then multiplied by 1, 2, 3 until you get back to the same number, you're going to create a whole set of elements. And a generator is an element such that the set of elements you can get by doing this is the whole set of elements in the set. Fields that are not prime will have elements that are not generators. So for instance, if you look at a group of order 6, so like elements from 0 to 5, you will have elements like 2, that 2 plus 2 is 4, 2 plus 2 is 4 plus 2 is 6, which is 0. And so you get back to, so you can only generate 2, 0, 2, and 4 with 2. And what you find is that the groups you can actually, and this is getting to, I mean, now it's unrelated to all this, but it's kind of interesting stuff. The groups you can actually generate are groups that are going to have a cardinality that divides the order of your total group. So that's kind of a rule. I forget which theorem this is, but because the cardinality of any generation group divides the order of the total group, and your group is order prime in this case, the only way to have every generator is going to generate the whole thing. And this is true both for addition and for multiplication. What this means is that 1 times A, 2 times A, 3 times A are all going to be different until we get to P times A. It also means that a to the 0, a to the 1, a to the 2, a to the 3 are going to be different until you get to a to the p minus 1. That specific term one is Fermat's little theorem, which says that for a field, or I mean, like for multiplication, a to the p minus 1 equals 1, basically. So any element in any field, in prime field, if you put it to the power of p minus 1, you'll always get back to 1. And that's how we computed inverses earlier. You can use that fact to compute inverses in either fields that are of prime order, or in RSA. It's a little bit more complicated, but you can still use a similar effect. Yeah. Anyway, so this kind of goes much beyond what you need to know for this class. But to summarize, the reason why you could potentially extend this to do documents up to p minus 1 documents is that a squared times 1 to p minus 1 is always going to be different from 0, and so you'll never get back to your actual exponent that you do know. Does this make sense? Cool. And yeah, and I also encourage you, if you haven't taken a class on algebra and stuff like this, and you're interested in this stuff, I mean, I'm not saying it's very useful in life, but it's cool stuff. So if you like math, it's a fun topic to study. Thanks for coming to this review session. Good luck on the final. And yeah.
I realized we forgot to record.
I record.